Hi, welcome to another recitation. The topics for today are logarithmic and implicit differentiation. So I'm going to have three problems about each, 6 in total. And let's get right into it. This is the typical problem for logarithmic differentiation. We need to compute a derivative of what's called a tower function. It's a function raised to another. And I'm using some rather different notation here just for the purpose of we need to get used to this notation as well. Essentially what this means is, first of all, we want to find the derivative with respect to x, and then we want to calculate that at the number x equals pi over 2. So this problem is secretly just asking if f of x is the function sine x raised to ln x, then what is f prime of the number pi over 2? This is just yet another way to use a notation for this number. So okay, let's find f prime. Well, if f of x is sine x raised to ln x, you know that when you have tower functions like this, what you have to do is take the log on both sides, which is going to cause this exponent to go down in front of the log. So ln x times ln of sine x. That's the log of f of x. We're going to find the derivative of this expression because it's easier than the original function. So on the one hand, once again, this is the fact that you should always know, which is a consequence of the chain rule. Ln of f of x, when you take the derivative of that, you will always find f prime over f. So this is always true on the one hand. On the other hand, if we differentiate the expression that we have on the right side, what do we get? By the product rule, you need to take the prime of the first function and copy down the second, plus copy down the first function and take the prime of the second. This is the product or Leibniz rule. Okay, so computing this, ln x prime, this is the one that everybody should know, 1 over x, plus we have our ln x here, and then what is this other prime? Well, for this one, you're going to need a chain rule. I'm not going to write down the full procedure. We've been doing this many, many times now. So let's just try to think about how we obtain this derivative here by chain rule. You have an outer function, which is ln, applied to an inner function, which is just sine x. The derivative of the outer function applied to the inner function will give you 1 over sine x. And you need to multiply this by the derivative of the inner function, which is cosine x now. So this is what you get from the chain rule. Cosine times 1 over sine. That's what I'm writing here. You can also say cotangent. All right. This whole thing is supposed to be what f prime over f is equal to. So if you want to solve for f prime, you need to multiply by f. Don't forget this step. So this is the expression after multiplying by f. And what you want to do to finalize this is rewrite what f of x actually is equal to. The function was given in the problem, sine x raised to ln x. And then copy down the rest. But what is now f prime of pi over 2 going to be? Remember the question was asking for f prime of a specific number. Now that we found f prime in general, we can find this one. So you're going to see a lot of things will simplify here. Sine of pi over 2 is 1. We need to raise 1 to ln of pi over 2, whatever that number is, doesn't matter. It's not 0. I mean, even if this was a 0, this would still be a 1 raised to anything. And now 1 over x, if x is pi over 2, 1 over x is 2 over pi. And in here we have ln of 1, so that doesn't matter either because this ln of 1 will be a 0, plus ln of pi over 2 times, once again, a 0. cosine of pi over 2 is 0, sine is 1. So you see that this term is 0 because of that 0. This term here is 0, ln of 1. So the whole thing is just 0. This function has a 0 derivative at this number, pi over 2. And that finishes the problem. Moving on to the next problem. This is kind of a tricky one. With the function is secretly simpler. And I'm going to explain this after, but I'm going to first solve the problem, imagining that we don't see a simplification that happens here. Find the derivative of this function. Once again, a tower function. So we're going to just apply the procedure blindly to see what happens. We have f of x. We want to take ln of f of x. So the 1 over ln x is here outside of the ln. And then the ln happens only at the base term, 1 over x. It is right here that if you think about this carefully, you should see a simplification here. But let's imagine that we don't see it. I'm spoiling the surprise. All right, so the next step after taking ln, we want to find its derivative. Always write this down. On the one hand, this derivative is always f prime over f. But on the other hand, you're going to take this derivative now. By, again, the product rule. This is what I'm writing down. So I had a product of two terms. I'm taking the derivative in each one of them separately and adding the results. Now we have to compute this. Each one of these derivatives will require some sort of rule for you. The first one, I'm actually, well, at least I'm going to indicate what you can do with this guy. 1 over ln x prime. What you can do here, either quotient rule. It's a simple form of the quotient rule because, well, it is a fraction, but the numerator is a constant number, just 1. So that would be very easy. Or you can do this by chain rule. If you regard this as a composition, the inner function is ln x, and then what you're doing with that later is taking its reciprocal, 1 over that. So you can have this type of chain rule here, inner function ln x, outer function 1 over that, and try to see what happens there. As for the second term, this one is chain rule. If you don't simplify the ln of 1 over x, then that is a function of a function, so you have chain rule here. It works differently from the previous one because this time 1 over x is the inside function, and then you're taking an ln of that. So ln of u is the outer function. You see that it's reversed compared to the previous one. So it's going to give you a different derivative. But anyway, I'm just indicating how you could solve these derivatives. And I'm going to write down the answers for them. The first one, let's see, if you're going to do this by the chain rule, derivative of ln x is 1 over x. And the derivative of the outer function, which would be 1 over ln x, would be minus 1 over that squared. The derivative of 1 over x is minus 1 over x squared. And that would be your outer function in this case. I guess I should probably start with that term, multiply by 1 over x. That's usually the order that we do things in the chain rule. Of course, it doesn't matter. But all right. So you have this plus 1 over ln x. This term is this one up here. And now this derivative of the function ln of 1 over x, how would that go by the chain rule? So the derivative of the outer function is ln. That will be 1 over what's inside. And what's inside is also 1 over x. So 1 over x is just x. And you multiply this by the derivative of the inner function, 1 over x, which is minus 1 over x squared. So now we have this expression. This is not your final answer yet, because this was a logarithmic differentiation problem. this expression is actually equal to f prime over f. When you want to then solve for f prime by multiplying by f of x, let me just write dot 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 here. And now when I write down my actual final answer, which is plugging in for f of x, the actual expression for it given in the problem, 1 over x raised to 1 over ln x. And now I'm gonna rewrite this parentheses, this dot dot dot. So minus 1 over ln x squared times 1 over x times ln of 1 over x plus 1 over ln x times minus 1 over x squared. Now, okay, if the question never asks you to simplify anything and you're not gonna use this later for any purpose, then you should leave it like this. This is the final answer. Though if you wanted to simplify this, there's many things that you can do here. But let's not simplify it like here in this way. As I said, this is a final answer. But I wanted to point out now what I mentioned in the beginning, another solution, that there is a simplification that we missed in the beginning that would have made our life much easier. Let me just start the problem over again. So remember that we were trying to find the derivative of this function, this f of x. I'm going to find once again ln of f of x. This is how you would start the problem anyway. Well, but now if you remember your properties of logs, ln of 1 over x, or in general ln of any quotient, is equal to the difference of the ln's of numerator and denominator. And ln of 1 that you obtain here is 0. So this is actually 1 over ln x times minus ln x, which is minus 1 if you cancel the ln's. Ln x is, I mean, in general, for x different from 1, this number is different from 0. We are already assuming ln x is different from 0 in this problem because, well, we have it in a denominator up here. So it's fine to cancel them, and you get to the conclusion that ln of f of x is actually equal to -1. So after seeing the simplification, if you would then proceed with the problem, after finding a derivative, once again, derivative of ln of f is always f prime over f, but the derivative on the right side is 0, the derivative of -1. So you see this is much easier now. F prime is f times 0, which is 0. That's the actual final answer. This whole expression that we had up here, it needed to simplify. There are simplifications just like the one we just did with ln of 1 over x. If you plug that into here, you should see this is a 0. So I just wanted to call your attention to the properties of log. Just because the question is not explicitly about that doesn't mean you don't need to realize that it makes your life easier. By the way, this function is a constant function because the derivative is 0 everywhere. That means the function is just a horizontal line, a constant function. No matter what x you have, this number is always the same. And it is 1 over e, I believe. But anyway, let's move on to the next logarithmic differentiation problem. A standard one, once again, uses log differentiation to find f prime of 0 for this crazy mess of a function. You definitely don't want to find the derivative of this using the quotient rule, but the log, using logarithmic differentiation will make your life much easier. What is the log here? We need the log of the numerator minus denominator. And when you take log of the numerator, that's a product of two terms. So those two will get combined in a plus. So like this, log of, by the way, when I say log or when I say ln, I always mean ln, the natural base logarithm. So it's like this. Log of the first term plus log of the second term minus log of the denominator. And furthermore, each one of these guys has an exponent that we can bring outside of the logs. In this case, 1/5, 1/3, and 2/3. Now taking a derivative is much easier in here. ln of f of x prime, on the one hand, always f prime over f, but on the other hand, differentiating the right side. How do you take ln of x plus 3? Well, that's a chain rule. You do have an inner function, which is x plus 3. However, the derivative of that inner function is 1. So when you apply the chain rule here, I mean, first of all, you have this 1/5 in front, but after that, this is the derivative of the outer function, ln, which is 1 over the inner function. That's what I'm writing here. And you need to multiply this by the derivative of the inner function, but that's just a 1. So this is the derivative. A similar thing happens in the second term, but you need to be careful about this third term here because of the 2x inside. A lot of students would make the mistake of saying that the derivative on the third term is just 1 over 2x plus 1, but it's actually 2 over that. So once again, chain rule. 1 over 2x plus 1 would be the derivative of the outer function applied on the inner function. But then you multiply that by 2, which is the derivative of the inner function. If you don't see how to do this in one step like this, you can always just use our procedure of calling u the inner function, y the outer function of the inner function. You know how that works. I hope. Anyway, here is f prime over f. Let's not simplify this. Let's not put these fractions together. We don't have to. But this is not f prime yet. F prime is f times this. And what was f? We had our f in the beginning here. It's this mess of a function. X plus 3 to the 1/5. X plus 2 to the 1/3 over 2x plus 1 to the 2/3 times, so this was f, and now we're multiplying by the derivative that we just found. And here you have f prime. Well, so 4/3. I guess we can write it like this. I'm multiplying the 2's together. This 2 times 2 up here became this 4. All right, this is f prime of x, but the problem wanted f prime of 0. That's very easy to find in here. Just plug in 0 for x. So you do have this crazy term in your fraction. 2x plus 1 becomes just 1, and 1 raised to 2/3 is just 1. But now inside here you have 1/5 times 1/3 plus 1/3 times 1/2 minus 4/3 times 1. So probably you want to leave it like this, or maybe, 3 to the 1/5 is the same thing as 5th root of 3. Here you have the cubic root of 2, cube root of 2. And if you want to combine these fractions into just 1, you can. I'm not going to do that. This should not be our biggest concern here, simplifying these fractions. But you should at least be aware that that's the thing you can do. Maybe the question will, instead of ask you to write down the answer, they will give you some options and you have to find the correct answer, and it might be in this form. So that's why I'm writing this. So we're going to move on. It's enough with log differentiation. There isn't much secret to that. And the same is true about this other topic now, the implicit differentiation. We are going to have problems now that are like this. I'm giving you an equation for a function of another variable, usually y, a function of x, but the equation is implicit. You have x's and y's everywhere. So let's read about this one. The problem is find the equation of a tangent line, and the curve is called a cardioid, by the way. If you if you use a computer to graph this crazy expression, what you find is it's not a graph of a function, it's a general curve that has this heart shape. So it's called a cardioid. And the question wants us to find the equation of the tangent line at the point where this curve is crossing the y-axis on the positive y side. So I marked this point up here on the y-axis. You can see that the derivative line is this, the tangent line, sorry, is this green line that's sloping down. So if we're going to regard y as a function of x, then this has a negative slope. Let's try to find it out. So y as function of x. That is usually the case, usually what you want to consider. And you can see that it's true in the curve, not everywhere on the curve. The curve fails the vertical line test, but if you are close enough to the point where you are interested, then this is a graph of a function. For example, if you take only the upper half, this is the graph of a function, and it's y as a function of x. You could also do this with x as a function of y, by the way, but it's more complicated. We haven't seen that, so you should always try y as a function of x. Not more complicated, I mean, but just we are not used to it. It is all the same, of course. So, okay, what we're gonna do is take a derivative of the whole equation, but it's implicit. So what I always recommend you do is, first of all, write down, instead of y, you write y of x, like this. So that you're really gonna remember that when you're taking a derivative with respect to x, some of these expressions are implicit functions of x. So we're gonna take a derivative now with respect to x. Taking d dx, this becomes what? So what is the derivative here? First term. You need a chain rule for this. You have something squared, so the derivative would be 2 times that thing, that inner function. But you need to multiply this by the derivative of this inner function. Derivative of x squared plus y squared. Well, that would be 2x plus, how do we differentiate y squared? That's once again a chain rule. The derivative of the square of something would be 2 times that thing. But you multiply by the derivative of the inner function, which is the y function in this case. So this entire term came from the chain rule for this first term of the equation. Next term, this one requires the product rule. If you differentiate first the x outside, you just get 4 times the other function, which is x squared plus y squared. And if you make the prime act on the second function, x squared plus y squared, then the derivative of that, we already computed it right here. It's 2x plus 2y y prime. This is the derivative of the left side of the equation, this whole expression. And on the right, you have 4y squared. Differentiating that will give you 4 times 2y times y prime. Now I'm just gonna, well, I guess we can leave it like this. The question, as a reminder, the question was not asking us to find a formula for y prime in general. Like you could solve for y prime from here now, but there's no need to do that. We actually want to find the equation of a tangent line. We knew that we had to differentiate, of course, but now let's try to think what we need to do. First of all, we don't know what this point is. I'm scrolling up. What is the point going to be, actually? It is a point on the curve, but nobody told us what it is other than it is where the curve is crossing the y-axis on the positive y side. What is the y coordinate here? We should try to find that. And that actually fits up here, finding the point. Whatever this point is, it must satisfy the equation of the curve. And we know that x is equal to 0 on that point, because it is on the y-axis. So what happens if you take x equals 0 into this equation? X equals 0. it simplifies a lot. You're going to just have y squared square, so that's y to the fourth, plus the entire second term is a 0 because of this x. And then the right side is for y squared. You see that this is going to simplify. If you divide by y squared, you have y squared equals 4, so y is plus or minus 2. We are on the positive y-axis, y-axis side, so by default it is the plus 2. So we now have the coordinates of the point. This is the point 0, 2. All right, obtaining the point on a curve is always by using the equation of the curve. And now you're good. We do have the coordinates of the point 0, 2. The very last thing that you need now is y prime of 0 in order to find the equation of the tangent line. We want to find the derivative when the point is 0, when the x value is 0. So we're going to plug in 0 into this equation right up here, this one, because this is the equation that contains y prime, the number that we want to find. So plug in x equals 0, and I guess y of x will become 2. And the equation, we know this, right? The y coordinate of the point that we are interested in is the number 2. We just found that. So plug this into this equation. What does that give you? So 2 times 0 plus 2 squared times 0 plus 2 times 2 times y prime of 0, that's right here, the number that we want to find, plus 4 times 0 plus 2 squared, this is here, should be equal, sorry, there's another term here, but that's just a 0, 4 times 0 times whatever, x is 0, so this term is actually not in there. All of this should be equal to 4 times 2 times y of 0 is 2 times y prime of 0 that we want to find. So now just simplify, clean this up. 2 times 4 is 8 times inside here 4 y prime of 0 plus 4 times 4 16 equals 16 y prime of 0. So on the left you have 32 y prime of 0 plus 16, and on the right 16 y prime of 0. Isolating the y primes and moving the 16 to the other side, you will find y prime of 0 equals -1. This is consistent with the figure. If you remember the drawing, the line was sloping down, and we found a negative value for this derivative. Now, tangent line, you have everything you need. It is always y minus the y coordinate. This was y of 0 equals this slope that we just found, y prime of 0, times x minus, well, the x coordinate, that's just the x coordinate of the point. It was 0. So you have y minus 2 equals minus x. This is the equation of the tangent line. So what's the important thing to take from this problem is that notice that we only plugged in the actual value of the point. We knew x was 0 on the point, but we actually only plugged that in after differentiating the original equation of the curve. I did not plug in the value first and then differentiate. That's bad. You never do that. A derivative is something that you need to take. If you're going to be using derivative rules like we did, then you can only do that for an equation that's valid on an entire open interval in general. So you need this to be valid essentially for all values of x. You need an equation that was valid for all values of x before you take a ddx. So if you had plugged in 0 already into the equation and then try to find a derivative, that's meaningless. So I'm going to move on. I have a similar problem here. I took this from the book. It's going to be basically the same thing, except for this twist of item B. So we'll see. The curve described by the equation y x squared plus 4 equals 8. This is called the witch of Agnesi. Find the equation of the tangent line to this curve at the point with y equals 1 and x less than 0. And they're saying find it in two ways. Item A is what we just did here, implicit differentiation. B is actually solve for y first and then find the derivative explicitly. But we're going to do A first. So I have the curve here. It's the red line. And the point that we are interested in is the point with y equals 1. So here it is with negative x this time. The tangent line is in green. You see that it's sloping upwards. This time we expect to find a positive slope. So let's do that. Here is the equation again, y x squared plus 4 equals 8. Before taking a derivative, let's find a point. I mean, you can do this in any order, as long as you take the derivative of the correct equation. Finding the point, the coordinates of this point. What we know about it is that y equals 1. We've been told that, and also x is negative. So plug in y equals 1 into the original equation of the curve. 1 times x squared plus 4 equals 8. So x squared plus 4 is 8. X squared is 4. X has to be negative 2 because they told us x less than 0. So the point is negative 2, 1. We're definitely going to need that later. But now you go back to the equation of the curve and you find the derivatives implicitly as y as a function of x. So maybe rewrite this as y of x, x squared plus 4 equals 8. So you remember. And again, this is the point that I was making in the previous problem. You do not want to plug in the point coordinates here. Like maybe you were inclined to plug in at least the one that you knew, y equals 1, right here, and then take a derivative. That's bad. You don't take a derivative after plugging in the points, because that would be meaningless for you. You need to take the derivative of the original equation. So that's exactly what we're going to do here, ddx. Well, this is an easy one to find by product rule. You get y prime times x squared plus 4 plus y times derivative of x squared plus 4 is 2x. And the derivative of 8 is 0. Be careful with this. Students tend to forget that taking a derivative on the, if you have just a number on the right side, it becomes 0. This is an equation that is valid for all points, x's and y's, on the curve. But now we can plug in the specific point that we have, negative 2 and 1. So if you do x equals negative 2 and the y value, y of x is 1, this becomes y prime of negative 2 times x squared plus 4 is negative 2 squared plus 4, plus this y of x here is y of negative 2, which is 1. And then 2 times x equals 0. So cleaning up, the number that we want to find, the derivative, times 8 minus 4 equals 0. So 8 y prime of 2 equals 4. Y prime of 2 equals 1/2. That is the derivative. With this, you find the equation of the tangent line. Y minus the value of y on the point is equal to the slope. I'm just indicating what they are right here. Yeah, I kept writing 2 in here. I meant negative 2 in parentheses. I'm going to correct that in red. These are negative 2. That's the actual x value of the point that we want. So here -2 and then times x minus, what is the x value? -2 once again. So the answer, instead of x minus -2, I'm writing x plus 2. But you know, this is a valid answer. This was item A. B is going to be very similar. Let me go back up so we can look at what B was saying. B is solve for y and then differentiate directly. Because as it turns out, this equation, differently from the previous one, this one can be differentiated, can be solved for y very easily. You just divide by x squared plus 4. And you have the function, the expression. So I'm going to do that first. Solve for y. Well, y is dividing the right side, which was just 8 by x squared plus 4. This is y. Now this is an explicit function. And this is a problem that we already know how to solve from previous lectures. If somebody gives you a function, think of this as f of x, and you want to find the equation of the tangent line to a certain point, where we already knew x was -2, by the way. This is the same, the point that we are interested in. We find this the same way. Now, what is the equation of the tangent line to the point x equals, at the point x equals -2? Well, you're gonna need to find the derivative of this expression. So let's find that. Derivative of this expression. Maybe we're gonna use the quotient rule here. Or you can do this by chain rule as well. So I'm just writing low d high minus high d low over low square. But you see that whenever you have fractions where the numerator is a constant, the first term just disappears. 8 prime is 0. So what is actually left is minus, in this case, minus 16x divided by x squared plus 4 squared. This is the derivative, y prime, or you can say right here, I'm going to say y prime of x to be more consistent with our notation. So if you need y prime of 2, sorry, -2, what is it? Well, -16 times -2 divided by -2 squared plus 4 squared. So at the top we have a plus 32. And at the bottom here you have 4 plus 4, that is 8 squared, which is 64. 32 over 64 is 1/2. Now the rest is the same, of course. You see that we have the same value for the slope, 1/2, as we just found. I'm just writing the final answer, the equation of the line. But the important point that I wanted to show is that you get the same slope that you got from implicit differentiation, 1/2. Now, yeah, of course, this is not always possible to do. This was a very easy equation to solve explicitly. The previous one really was not possible. Now, moving on to the next problem. This is the last one. Suppose that you have this very simple equation between x and y. Find an implicit equation for the second derivative. This thing here, by the way, in symbols, this is the same thing as y double prime of x in terms of x's and y's only. I don't believe we've done anything like this, but it's really the same technique as implicit differentiation. After you find one implicit and you solve for y prime, you just take a derivative of that again. So we're going to see that. The equation is e to the y equals x squared times y. I'm including the parenthesis x to remind us what is a function of x. Let's take one derivative, d dx. By chain rule, derivative of e to the y is e to the y times y prime. That is the derivative of the outer function times the derivative of the inner function. This should be equal to, this right-hand side term goes by the product rule. 2x times y plus x squared times y prime. Let's solve for y prime here before we take another derivative. we should do that. If you're trying to take two derivatives in an implicit equation, that's usually what you want to do. So first of all, I'm going to erase the parenthesis x now, so we have a cleaner equation like this. How do we solve for y prime? It's always like this. You want to group together the y prime terms and factor them. In this case, you have something like this. So I basically moved the x squared y prime term to the other side. And on the right, you just have 2xy left. So solving for y prime gives you 2xy over e to the y minus x squared. This is one derivative. We're going to save this expression for later. But what we're going to do with it now is find another derivative, because that's what we wanted to do. We wanted to find y double prime. So taking two primes now, taking out one prime of this expression, that is once again an implicit differentiation problem. This time we're going to use the quotient rule here. So I'm writing it down. Low d high minus high d low. You see that I did not write the parenthesis x this time. You could have done that. It's just that it would be too large of a formula. Over low square. We need to find these primes in the numerator here. So what is 2xy prime? Well, by the product rule, 2x prime is 1 times y plus 2x times y prime. Y prime is not 1, y prime is y prime, because it's a prime with respect to x. So that's that term. Second term here, derivative of e to the y minus x squared. E to the y becomes e to the y times y prime, just like before. X squared becomes 2x over e to the y minus x squared squared. So this is a formula for y double prime. The only problem with it is that it includes not only x's and y's, but it also includes y prime in itself, 1 prime, as it normally does. But that's really not a problem for us because we already know y prime. We do have a formula for y prime involving only x's and y's. So that's why I said, let's save this for later. This is the last step that we need now. Just plug this crazy expression for y prime. So 2xy over e to the x, e to the y minus x squared. So I'm plugging that for the two instances of y prime. It's right here. And the second one, 2xy over e to the y minus x squared. And now this is a formula for y double prime involving only x's and y's. Which you probably don't want to do anything with it. Let's not simplify this. This is the answer to this problem.